Okay. Some of the things that we might skip faster in the previous part, I want to make sure. For example, we use ceiling here. Okay, what is ceiling doing? You put any rational or irrational number in it, and it would give you its ceiling integer. Like it would fill it up until it becomes integer. Okay, 199, 2, 299, 3, 2, 0, 0, 0, 0, 0, 1, 3 again, right?
Is there another one for the floor?
Floor, I guess. Yeah. And there is int. No? Round. Sorry. There is round, which is like 49 is 2, 51 is 3. Okay? Good. What else you might have missed? The break comment here. And you didn't ask me, right? The break means that if this condition is met, if you are in this loop, then you break this bigger loop. So you don't wait for until you reach this upper number. You break the cycle and you go ahead with your calculation. That's yes.
The scope breaking, because I think in Java it breaks out of the whole loop. Like,
Yes.
Like only
This
the
is
smallest loop.
Only the smallest loop.
only the smallest loop. Yes, it actually breaks. No, it actually breaks the upper loop, which I don't get completely. What? Yes, yes, it breaks that one, but yes, it breaks that one because it's in it, right?
Because you can't break an if loop.
Yes, exactly, exactly. You're right. What else? CPU time gives you the CPU time. So we set time 0 to CPU time, then we just subtracted this. Another thing that we were carried away with this commenting out thing, and I forgot to explain this. So, okay, if I comment out this one and plot it, it will give you the plot that doesn't care about the scales. So you can see that this one goes from 1 to 100, so it's quite big. This one is small, but MATLAB just fits it in the whole plot. But if you make axis equal, right, then it does care about the scale. So 100 versus 1 is now properly scaled, right? But now you have this axis here. Okay. If you want to get rid of them, you also add off. So you get yourself nice thing without axis. We are recording. Very good. So what we were trying to do, let me not come up in this. For some reason it's, oh, oh, I always wanted to do this. Douglas Hofstadter is really, really happy somewhere. Do you know him? Yes. Okay. Now we have our iPad. Remember this? Okay. Do you have any questions so far? Yes.
You said the first one is 1 multiplied by 0, and the second one is 2 times by 1, right?
I said, okay, let me choose this one. So this 0 is multiplied with this 1. This 1 is multiplied by this 2. This 0 multiplied by this 4. So basically it gives you the corresponding number for its neighborhood. Okay. One final thing that I want to do is the following. So remember, it has another 0 here. Okay. So I want my original vector is this one, and if you take it over here, you can see that there is nothing here and there is an extra 0 here. I will do some magic to take it here and to take this one. Not magic, I know. Modic. I will use mod to take this 0 over here. And it will basically correspond to periodic boundary condition. In my end is my beginning. T.S. Eliot. Yeah. Okay. To do that, let's do mod 1 to 5 versus 5. What do you expect? Okay, I have to do 1 to 5. It's 1, 2, 3, 4, 5. Okay. What if I do mod 1 to 5 with respect to 5? So you 1, 2, 3, 4, 0. Very good. Very good. What if I take plus 1? It's 2, 3, 4, 5, 1. And compare it with 1, 5. It's this one going all the way there, and the rest shifted to the left. Okay. So I will write down here NE, okay, meaning negative, okay, mod 1 to n, okay, this is, this is positive. This is shifting things towards left. This is looking at the right-hand side of the neighborhood, right? So let's run this one. So you choose something and you press F7. And you can see that it goes all the way from 1 to 100 and then ends with 0, right? But if you do plus 1, then you get whatever we did for 1 to 5, right? Now, what about the negative one? So what if I want to have 5, 1, 2, 3, 4? Do you understand the point? 1 to 5 is this one. Mod 1 to 5, 1, minus 1. I don't like it, right? We don't like it. What we do is we remain, this is still plus 1, but we subtract minus 2 from here. Okay. MATLAB understands it as 1 to 5 minus 2, but we're doing 1 to 5 minus 2. So it's 5, 1, 2, 3, 4. Are you with me still? Yes? You didn't understand this one or the previous one? Let's do the previous one. This is okay, right? What if I do plus 1 to this vector? It's 2, 3, 4, 5. Then 1 is here. And what we do next is we take this 1 to 5 minus 2. which gives you, okay, let's run this one. This one gives you -1, 0, 1, 2, 3. But 0 mod 5 is 0, right? +1 gives you 1 over here. -1 mod 5 is 4. Okay? +1 gives you this 5. No? Should I continue or not? So I will do it here, -1. I don't have enough time to do Game of Life maybe, but never mind. Okay, so I want to make something. For example, let's have a new vector. Let's comment this out for now. Let's have a new vector that has the second row, all of its second row is P. Okay. All of its first row is which one? The negative one, like 1 to n is P, but with negative indices. And the third one is P with positive indices. Let's run this and see. Okay, I have to comment this. See how C looks like. And let's make it not 100, but 11. Okay. So I will click on C. Okay, I have to make it 3. Run it. Okay, let's look at 3. Okay, I have to do it 2. There you go. Do you see that we get what we wanted to get? Like in the middle, the actual thing, then this one is shifted, this one is shifted, etc. Are you with me still? Yes? So I will do one more thing. I will call D equals to, let me cheat. Okay. 4 times the negative one plus 2 times P plus, we already discussed this, do you remember? So the good thing with being a matrix lab is that you can multiply, if it's a reasonable multiplication of vectors, then MATLAB will do it for you, okay? So 4 times this vector plus 2 times this vector plus 1 times this vector. Let's see what D looks like. D looks like this. Do you see why D looks like this? For example, in the 6th place, you have yourself your 2. Do you remember the 2 that we derived? For the middle one? Yes. So you derive the middle one. Okay? Okay, let me see. I'm tempted to use the already finished code. Do you want me to go to the code already? I have the working code here. Yes or no? No.
How long will it take for that one to finish?
This one.
Yeah, if we were to
Yes, okay. Okay. Let me cheat again. Okay. Very good. So I want to write down another thing. R equals to 8 minus D. This is the final step, probably. What is R? R gives you 8 for all this, and it gives you 7, 6 for etc. Okay, we will come back to this in a moment. Let's remember our process of thought. Basically, I will calculate for each of these cells a number that is between, if you calculate this 8 minus D stuff, it's between 1 and 10, 1 and 8, excuse me, okay? And the rule number 30 is basically something like this. It's written in binary code, and let's say for 1, 2, 3, 4, 5, 6, 7, 8, it has something like 0, 0, 1, 1. Okay, I have to check. Do you remember? 0, 1, 1, 1, 1, 0, 0, 0. Okay? Do you see it? So let's write it down over here. R equals to how many zeros? 1, 0, 0, 1, 1, 1, 1, 0. Okay. So what I will do next is super tricky. Let's just take this 8 over here. There it is. So I have this D vector that is basically this 8, 8, 8 something. So what about R of D? What it will give me? Let's call it E. It gives me a bunch of zeros and ones, right? But how did we get this? R of D gives you zeros and ones. What is happening is actually, so for example, for the first element of D, it's 8, right? Since the first element of D is 8, the first element of E is whatever the 8th element of R is. Everyone gets this? Yes? Super. Awesome. You can also realize that it's already the next line that we have in the rule 30. Do you see? These 3 ones. It's already working. So let's then finish it up. So we start with some P, and okay, not erase this. Let's go from 4n equals to 2 to, let's go all the way up to n. Or let's start from 1 and go to n minus 1. The next thing that you have is actually this whole thing, okay, R of this whole thing, but not 1, instead we will have n, right? I hope it's clear to you. So so let's say n is 1, then we do all these things that we were doing for the first line of P, and after all is done, we get the second line of P. Then n becomes 2, we get the third line from the second one. If we run this, we get an error.
The end should be begin. No.
P and should be 2 times P and
P, which one?
2 times P is metric vector.
Ah, very good. Thank you. It should be n like this. So nth line, but without shifting. Wow. If we left P just like that, it would take the whole matrix. So there you go. MATLAB does whatever you want to do, unless whatever you want to do is stupid. Okay. Okay. Then we have ourselves our P that goes with zeros and ones. We are almost there. Let's plot this thing with 101. There you go. Magic. So you can see that it's really nice, and I will actually go to my original code that has everything in it. And basically, as I mentioned, rule 30 corresponds to the binary code of this one, right? So here in this code, you have this place where you take the decimal to binary. So you simply type rule 30, not 300, 30, and you get yourself something I didn't expect. Ah, okay. Well, I ruined my code before coming, so I have to heal it. There you go, healed. So rule 30 is this one, and we can make it even bigger, like 1000 steps. And for some reason, okay, let's go dig in. So you can see that you have order, but a very fragile one. And over here you have chaos, right? So what Wolfram did was playing with all possible rules. Like let's try 29. It's very close to 30, right? It couldn't be further apart though. Let's make it to 100 maybe. Then you can see the patterns clearly. So it's a quite boring game, right? What about 31? I can just put it down here, so we will not close it and open it all the way. So 32, let's run it. Nothing happens. 33, 34, No? Didn't run? 35. İzmir. 36. 37. Boring. 8. Cool. 9. Come on. Let's make it 50. Something nice. Well, I can't zoom when I do this, so what about 54? Not bad. 62. Interesting. 60. A fractal, right? We will come to this later on. Fractals. 90. Again, a fractal. And finally, 110. We should look different. Yes, it looks different actually. Let's undock this. So Wolfram discovered that you can see that this is something different. Wolfram discovered that there are 4 classes of this automaton. You cannot define this super quantitatively. It's qualitative thing, right? Let's read a little bit of Wikipedia on this. Okay, there it is. Sorry for being so, lazy. I could have taken this and put this on slides. But this one, okay. So class 1, nearly all initial patterns evolve quickly into a stable homogeneous state. Okay. Any randomness in the initial pattern disappears. By the way, we always started with 1, 1 over there, right? We could have started with randomness. And then you will see more clearly what these classes correspond to. So another one is oscillating patterns. The third one is chaotic. And the fourth one, so the third one, a good example is rule number 30, right? It has chaos in it. So anything that appears disappears really quickly at random. Do you understand? But rule 110 is actually really interesting. It has this has been proven for rule 130. Okay, it's this automata capable of universal computation actually. Okay, what is universal computation? I don't know, but it's something. Whenever you get it, it's really, really important. Well, the good thing is that it connects with nature. So basically, the idea of 4 classes can be taken to dynamical systems and can correspond to systems in thermal equilibrium, uniform systems, chaotic systems, and complex far from equilibrium systems with dissipative structures. Okay? All this will make more and more sense as we go along. Okay? Okay. Can someone speak for 3 or 2 minutes? Need some rest. Who wants to speak? You speak. Tell me something. Do you understand everything? Most of the things. Was it super boring?
No, it wasn't. I was interested in those fractal structures.
Yes, we will come back to them in the 3rd week, I guess. The geometry of nature. We will swim in fractals those week, in that week. We will find that they are not one-dimensional or two-dimensional. They are, I don't know. Okay, go ahead.
I didn't understand what we changed with the rule 30.
Okay. Very good question. So what you change with the rule 30 is the following. So rule 30 would tell you that it's... Thank you very much. Something like this, right? And if you calculate this number in binary code, I mean, if you transfer this binary number to a decimal number, it's 30. So rule 31 is this one. Meaning that in the rule 30, if you have this one, it becomes 1 here. The rule 31 has 1 here. Okay? Okay. So, just to make sure that we are not doing something that is just fun, I want to show you a nature cover from 1984, before I was born actually. It's Cellular Automaton, of course, by Stephen Wolfram, and it's published in Nature as cover. And do you need more motivation? No, right? So you can see all these groups, like classifications there. It's serious business. And it didn't stop there. He wrote this, all kinds of things. Is this also his? Okay. Universality and complexity in cellular automata, etc. What is this one? Okay. Before we move to Game of Life, we will also check out Game of Life today, which is this one. I want to prepare you. Okay, this slide apparently is not so accidental. Let's just read this paper that appeared on the cover of Nature, this time very recently. 2017, I believe, yes. 13th April 2017, Nature cover. And what they realized is that a living mesoscopic cellular automaton made of skin cells. And let's read this beautiful passage. Using numerical simulations and mathematical derivation, we identify how a discrete von Neumann cellular automaton emerges from a continuous Turing reaction diffusion system. So these two guys that appeared in one slide appear here in one sentence, right? And cellular automaton in general, whatever we do with these grids, you can trace it back to von Neumann. And reaction diffusion, we will come to this in, I don't know, 7th or 8th week in the subject of living together, okay? So this is a lizard that has these nice patterns. Of course, here the cellular automaton is done on hexagons, okay? You usually see hexagons instead of squares in nature. And it's a serious business. So, blah, blah, blah. I can share these papers with you if you want. Do you want them? You want them? Okay. So let's now try coding this one, Game of Life, okay? Let me tell you first what it means. Again, this time you have two-dimensional mesh of ones and zeros, and 1 means alive, 0 means dead, okay? You can come up with all kinds of rules, but the most famous one is due to John Conway. And he was inspired by biology when he constructed these rules. Any leaf cell with fewer than 2 leaf neighbors dies as if caused by underpopulation. So what do we mean by neighbors? We mean these 8 cells around this one. Okay? If there are less than 2 ones around it, then it dies. Any leaf cell with 2 or 3 leaf neighbors lives on to the next generation. Is it clear? Any leaf cell with more than 3 leaf neighbors dies as if by overcrowding. Clear? And finally, any dead cell with exactly 3 leaf neighbors becomes a leaf cell as if by reproduction. Okay? So now we want to code this. Okay? Clear. Are you sure you don't want to see already coded one?
I don't think we have time. Well, we have 15 minutes.
Yes. There are tricky parts indeed in this code. So let me open the game over here. It's written only in 10 lines if you ignore all the rest. So, do you remember what this was? Mod n plus 1, etc. Do you remember? It would shift to the left, right? You also do remember what this was, right? So let's look at this line, what it does. It takes the ceiling of random numbers, n by n random numbers. So if I do rand 2 by 2, then I get 2 by 2 of random numbers between 0 and 1, uniformly distributed, okay? Now this time you get n by n random numbers. And what happens if I multiply it with 1.1? Let's make a bigger one, 5 by 5. Some of them are bigger than 1, right? And this ceiling would put those bigger than 1s to 2, right? It would fill it up to an integer. The smaller than 1s will be filled up to 1, right? And what do you get if you say minus 1? 0. So let's run this part. And you get an A that has zeros and ones. What does this 1.1 is doing? It's making sure that you get approximately 10% of the ones and the rest is 0, right? If you increase this up to 2, then you get half zeros, half ones. Okay? Makes sense? Makes sense. Very good. Then, what?
No, he was just unknowingly hitting high chairs.
Okay. I think, okay, maybe I should erase this one. I'm taking a big risk right now. I hope it works. 2, 3. Let me see if it works. It will. No, it's not working. I will put it back and think about it later on, but okay, this is working. So, what is this line doing? Yes, exactly. It's taking the left. Okay, let's say, let me draw it. Let's say you are interested in this cell, then what A negative is doing is looking at this cell, right? It's left and left. A negative blah blah is looking over here. A negative positive, this one is looking over here, etc. Right? And if you sum them up, basically what I'm doing right now in that code is I'm summing all the neighbors and also itself, summing all the numbers, okay? And I get some matrix B, right? So what is this line? This line is so beautiful. I can't, you know, I have to explain you what this means. So let's write down a table. So this is the value of B, right? Which corresponds to all the sums of the cells over here, okay? So what if B is 0? What is the next population? B is 0 means 0, 0, 0, 0, 0, 0, 0 everywhere. So what will be the fate of this one? 0, right? Let's call this A n plus 1. Then in the next generation it will be 0, right? You are quite bored, but I'm sorry. What about this one? With 1. Then you could have 1 in the neighborhood, like this. Or you could have had it like this and no neighborhood. Either way, it will die, right? So 0. What if it is 2? 0. Just trust me. What if it's 3? If it's 3, then you could have like 2 neighbors and 1 in between, 1 in the center. Then according to the rules, this lives on, right? What about this case?
It also does.
It also lives up. Actually, it is resurrected or 1, right? What if it is 4? If it's 0 and the 4 neighbors are over here, then it becomes 0, right? If it is, do you still see it? Yes. If it's 1 and it has 3 neighbors, then it becomes 1. Okay? Then whatever this one is, it stays the same, right? So it is AN in the previous generation. What if I do 5 neighbors? Just trust me, it's 0 afterwards, okay? Do you trust me? 6, 7, 8, 9. Doesn't matter, it's 0. So you can see that if B is 3, then it is 1. If B is 4, then it is A. Okay? And that beautiful line of code is doing exactly that. So if you type something like this, okay, let's make it 10. Let's make this 1. So let's say you have B which is like 1, 2, 3, 4. It has all the numbers in it, right? If we write down b equals 3, then it will give me zeros except where b is 3, and wherever b is 3, you will get 1. Okay? So wherever b is 3, you get 1. Do you remember our rule? I should like juggle this. Okay, there you go. For 3, you get 1. If it's 4, then you get a, whatever a is. You can see that the multiplication will take care of it. By the way, what is this little dot here?
You're doing a dot product of
Exactly. If I didn't put that dot, it would just multiply matrices, which would be quite different kind of thing that we want, right? Rows times rows, etc. We just want to multiply element-wise whatever we get from here with this one, okay? So if you run this code for, okay, then you have a thing of beauty that is a joy forever, right? This one from Keats. Okay, so what do we see here? Why do we call this game of life? At this point, maybe you should make some comments. What do you see here? How do you understand this? Anyone?
It's like the cycle of life and death.
Hmm?
It's like how nature operates.
It's like how the nature operates. Can you elaborate why it looks like life?
So because you have in some places there are, I don't know, these shapes that are being produced,
Mm-hmm.
and eventually they die off and move to some other region.
Mm-hmm.
Right. So it represents in time as something which is moving on.
Mm-hmm. Yes, all of the above is true. And you can see that at some point it will stop. Yes, this is our point where we stop. And this is indeed one of those class 4 objects, right? It's dissipative. It goes, it's surprising. It has this element of surprise. And it goes to some structures that are defined by laws underneath. And these particular structures are there because they can reproduce themselves, right? And we had, okay, again, I'm lazy and I will open you a Wikipedia page of this one. So you can have all these kinds of different constructs with game of life. Of course, you need to be really precise. If I add something over here, it will mess the whole thing up. It's not that stable as life is, but it's a game, right? So you can see that you have this. This is another way of reproducing itself only by shifting itself, right? So you can see them as moving objects. Puffer breeder. We have already seen this. There is nice like zoology of these guys. So still lives. We have seen all of them in the first run. Did you see? This one, this one, this one, this one. These are, and then there are blinkers like this. There is a pulsar, really nice structure. And there is this pentadecathlon that has a period of 15. Okay? And people really went crazy with this. Like there are,
I think there was something called die hard users.
Yes. Okay. What it means? It means that, okay, let's find it. Die hard. It means that if you start with this structure, it dies really hard. I mean, like, it takes like 1,000 steps for it to come to an end. Okay. Game of life on torus, periodic boundary condition, which we already did, right? Because we are taking these negatives and positives, which is cool. And a Turing machine made of game of life. This is the 6 octillionth step of it. And of course, my favorite one over here, life in life. You remember it from the previous one. Okay, I think we should stop here.